You ever wonder how we predict the future? Not with a crystal ball, but with data. We use it for pretty much everything, right? From figuring out the yield of a chemical reaction to forecasting the water quality after a big storm. Okay, let's dive into this. Because it turns out data has two very different personalities, and knowing which one you're dealing with, well, that's the key to unlocking all of its secrets. So that brings us to the big question. Is all data really created equal? And the answer is a hard no. Absolutely not. See, the type of data you have, its fundamental personality, is what tells you exactly how you can model it and what kind of future it can actually predict. And this slide right here, it perfectly captures the two worlds we're going to explore. On one side, we've got the world of tables. Think of this like a photo album, full of individual portraits where each picture tells its own complete story. But on the other side, you've got the world of timelines. This is way more like a film strip, where the order of the frames is everything. If you scramble them up, the whole story just falls apart. All right, let's start in that first world, the land of tables. This is where you'd find things like a big database of materials properties, or tables full of reaction yields under different conditions. It's structured, it's organized, and it has one really, really important characteristic. And that characteristic is independence. Every single row in the table is its own little self-contained story. What happened in experiment number 5 has zero direct influence on what happens in experiment number 6. They're all just individual portraits, just like in that photo album analogy. So how do we go about building a model here? Well, we follow a pretty clear progression. We always, and I mean always, start with a humble baseline. This could be something ridiculously simple, like just predicting the average outcome for every new situation. From there, we might move to a reliable workhorse, maybe a linear model. And then if we need to, we bring out the big guns, these smart ensemble models like random forests or gradient boosting, which are pretty much the gold standard for this kind of data. Okay, so we've built a model, but how do we understand what it's thinking? For that, we use a cool technique called feature importance. It's basically like asking the model, hey, of all the ingredients you looked at, the temperature, the pressure, the catalyst type, which ones were the most useful for predicting the final result? And it spits out a ranked list of our most influential factors. But, and this is so important, here's a crucial piece of wisdom. Feature importance is just a clue. It is not a definitive scientific law. It shows us what's correlated, but it absolutely does not prove causation. It's our job as scientists, as thinkers, to take those clues and figure out if they actually make sense in the real world. And now let's hop over to our second world. Welcome to the flow of time. This is where you find all that data from environmental sensors or from process monitoring in a factory or even chemical kinetics traces. Here, time isn't just another column in a spreadsheet. It's the very fabric that holds the entire story together. The main idea here, the central theme, is memory. What happened yesterday directly, and I mean directly, influences what's happening today. The quality of water in a river this morning is completely tied to its quality last night. Unlike our photo album, these data points are definitely not independent. Now this memory actually has a technical name, autocorrelation. Don't let the word scare you. It's just the mathematical way of saying that a value at one point in time is related to the values that came right before it. This is the defining personality trait of any time series data. And because of this memory, there is a cardinal sin in time series modeling. It's the one thing you can never, ever do. You can't just shuffle your data randomly when you split it for testing. Why? Because if you do, you're training your model on data from the future to predict the past. It's a huge mistake called data leakage, and it'll make your model look like a genius in testing, but be completely useless in the real world. So that brings us to the core challenge, right? How do we teach a model about the data's memory? How do we use the past to predict the future without accidentally letting it cheat and peek ahead? Well, the answer lies in some clever feature engineering. And this is the key technique. We explicitly create new features that represent the past. Just look at this table. For day 2, we make a whole new column called temp_yesterday that just has the value from day 1. For day 3, it has the value from day 2, and so on. We're literally giving our model a window into the recent past, which turns our tricky timeline problem into a simple table that a standard model can actually understand. And hey, we don't have to stop there. We can create all sorts of these time-smart features. Things like rolling averages, the average temperature over the last 7 days. Or features that capture cycles, like what day of the week it is, or the month of the year. We can even add special flags for known events, like a huge rainstorm that we know is going to impact the data. So we visited two very different worlds, right? The static world of tables and the flowing world of timelines. But across both of them, there are some universal truths, some golden rules that apply no matter what kind of data you're working with. So let's break down these golden rules. Rule number one, always start simple. Your fancy, complex model is totally worthless if it can't even beat a simple baseline, like just predicting that tomorrow will be the same as today. Rule number two, how you split your data for testing is absolutely critical. For tables, you shuffle. For timelines, you remember that cardinal sin, right? You never, ever shuffle. And rule number three, which is maybe the most important, you have to understand your data's personality before you even think about picking an algorithm.
Now, you might be sitting there thinking, okay, this is all pretty interesting, but why does it matter so much in the real world? Well, let me tell you, the stakes are incredibly high.
Because getting this right is the difference between a model that actually works and one that just fails spectacularly when you need it most. Understanding if your data is a collection of snapshots or a flowing river of time, that's what prevents you from making really costly mistakes. It lets you build predictive models that you can actually trust to make important real-world decisions.
So we've journeyed through the world of tables and the world of timelines, and we've learned to speak their unique languages. But this brings up a really fascinating final question, doesn't it? What happens when your data doesn't really fit either of those molds? What do you do when your data is a complex spectrum, a rich image, or even a sound wave? Well, that's a story for another time.